Right. So let me begin by reminding the result that we have established last time. So we have started studying invariant subspaces, right? So invariant subspaces. And we have obtained an important result, Theorem 521, which establishes a relationship between the characteristic polynomial of a linear operator and the characteristic polynomial of its restriction to an invariant subspace. Okay, so let me recall the statement of the theorem. So assume that V is a vector space, finite dimensional, and assume that T is a linear operator on V. Okay, so T belongs to L of V. Okay, and also let W be a T invariant subspace of V. Okay, so remember, this simply means that it's closed under the application of the linear operator T, right? Okay. So then, in this case, we can consider the restriction operator, right? So then we have TW, which is a linear operator on the subspace W, right? So then TW is the restriction of T to W, okay? And we have a connection between the characteristic polynomials of these two operators. So then the characteristic polynomial of TW, right? So characteristic polynomial of TW divides the characteristic polynomial of T itself. Okay, so we have this this nice relationship, and we saw some examples of this for a particular operator. And now, in view of this result, the idea that we may use the characteristic polynomial of TW, which is typically easier, right? Because the subspace might be small, for example. So you might use the characteristic polynomial of TW to gain some information about the characteristic polynomial of T itself. Okay. And for this, in order to use this idea, turns out that cyclic subspaces are very useful, because for them, we can obtain an explicit formula for the characteristic polynomial. Because cyclic subspaces are invariant subspaces of this particularly simple explicit form. So for them, we can calculate the characteristic polynomial explicitly. Okay, so how? That's the content of the next theorem. So Theorem 522, which deals with calculating the characteristic polynomials of operators on cyclic subspaces. So let T be a linear operator on V, and as usual, we assume that the dimension of V is finite. Okay, and also let W be the T cyclic subspace of V generated by some given vector. Okay, so let's say generated by the vector little v in the space capital V, and this vector little v is non-zero. Okay, let us denote by K the dimension of W, the dimension of this cyclic subspace. Okay, then we have the following two claims. A, we have that the set consisting of V, T of V, etc., T K minus 1 of V is a basis for W. Okay, so this first claim tells us that if the dimension of the cyclic subspace W is K, then we have this explicitly given basis for it. Yeah. So we just take the vector which generates it, and then we have to apply T several times up to Tk minus 1 of V. So altogether, this is K vectors, of course, right? Because we have V and then T of V, etc., Tk minus 1 of V. And we claim that this is a basis for W. This is part 1, okay? And given this basis, we can also determine the characteristic polynomial, okay? So if we have that A0V plus A1T of V plus etc. plus AK minus 1 T K minus 1 of V, okay, plus Tk of V is equal to 0, then the characteristic polynomial of the restricted operator TW is of the form f of t given by minus 1 to the power k times a0 plus a1t plus etc. plus a k minus 1 t to the power k minus 1 plus t to the k. Okay. So we have this explicit form for the linear operator. For the characteristic polynomial of the linear operator. Okay. So note that there exists some choice of the scalars a0, a1 through ak minus 1, so that the corresponding linear combination here is equal to 0, right? Because we know that the basis is given by the first k vectors, so v, t of v through tk minus 1 of v, okay? Hence, we must have there must exist some choice of the scalars ai like this, so that the sum is 0, right? Because tk of v is just another vector in w. So we must, so such ai exists. And then we can, once we determine such ai's, we can write out the characteristic polynomial explicitly using this expression, okay? So that's the point of this theorem. It allows us to calculate characteristic polynomials of operators restricted to a cyclic subspace. Okay, so first, but let's prove it. So proof. So first part, A, okay. So our task is to show that this is a basis. So since we have that V is a non-zero vector, remember, it follows that the set consisting of the single vector V is linearly independent. Yeah, so just triviality, okay. So now we take J be the largest integer, or positive integer more precisely, yeah. So positive integer such that we have beta consisting of V, T of V, etc. through Tj minus 1 of V is linearly independent. Okay. And such a J must exist, right? So note that such a J must exist because the whole space has finite dimension, right? So because the dimension of V itself is finite, okay? So it means that there can be only finitely many linearly independent vectors in V, okay? So if we keep adding vectors like this, we must get stuck at some point. You cannot add a linearly independent vector anymore, okay? So this tells us that such a J exists, yeah? Okay, so now let us take Z to be the span of beta corresponding to the largest J of this form, okay? Then we have that beta is a basis for Z, obviously, right? Because beta is a set of linearly independent vectors, and so it's automatically a basis for its own span, right? Okay, so we have that beta is a basis for Z, And moreover, we have that Tj of V already belongs to Z, right? Because again, J was chosen to be maximal with this property, right? So it means that if you try to add Tj to the set, to beta, then it would stop being linearly independent. But then it means that Tj of V already belongs to the span of vectors in beta. Yeah, and Z is the span of the vectors in beta. That's how we have that T of J belongs to Z. All right. So now we have to understand this Z a little bit. So the first claim is that Z is a T invariant subspace of V. Okay. So we know Z is a subspace, so we want to check that it's also T invariant in addition. Okay. So let's show this. Let me move to a new page. So let me repeat that claim. Z is a T invariant subspace. Okay. So to check it, we just use the definition of T invariance. So let W be any vector in Z. Okay. Since we have that by definition of Z, W is a linear combination of the vectors of beta, because remember, Z is just the span of beta, it follows that there exists some scalars, B0, B1, etc., through Bj minus 1, so all scalars in F, right? Such that W can be written as the corresponding linear combination of the vectors in beta. So we have W is equal to B0V plus B1 T of V plus etc. plus Bj minus 1 times the vector Tj minus 1 of V. Okay. So here we just wrote out that by definition of Z, it's the span. Let me see. There's a question in the chat. Can you explain why why TGV is an element of Z? Okay, good point. So the reason for this is that, remember, we chose J here to be the largest, right? It's the largest integer, such that this set is linearly independent. Okay, but then it means if I try to add J plus 1 to it, okay, so if I try to add Tj of V here, then this would mean, and it stays linearly independent, then it means that J wouldn't have been the largest with that property, right? Because then it means actually J plus 1 would also have this property. Yeah, this is the maximality of J. But if it means that adding Tj here to this set makes the whole set linearly dependent, but we know that the first vectors, these first vectors are linearly independent, so it means that the new vector is in the span of them already. Okay. Does this make sense? Okay. Now, the next question in the chat, why do you want to show that D is T invariant? Oh, okay. So here the idea is to, well, you'll see in a second, but the point basically want to use the characterization of of cyclic subspaces as the smallest invariant subspaces containing a given element that we discussed last time. So then we will use it to show that, in fact, Z is equal to W, okay? But you'll see it just in a second. So just go with me for this part for now. So first we show that Z is a T invariant subspace, right? So let's finish this argument. So again, we pick W, any vector in Z, and our task is to show that then T of Z is also in Z. Sorry, T of W is also in Z, right? That's what it means to show that the space is T invariant. Okay, so for this, we just write W as a linear combination of the vectors in the basis for Z. Okay, but also remember that T is a linear operator. So ST is linear. Okay, this means that applying T W can be written by applying T to the expression on the right-hand side. And here we use linearity, okay? So then we have that this is equal to B0 times T of V plus V1 times T square of V plus etc. plus Bj minus 1 Tj of V, right? So this gives us an expression for TW using linearity, okay? But then what do we get here? So this means that the vector T of W is a linear combination, right? Is a linear combination of vectors in Z, okay? Because look, this, and this are all vectors in Z. And for the last one, that this is in Z as well, we know this by what we just discussed, right? So this was this remark that Tj of V belongs to Z because J was chosen maximal. So then it means that each of these vectors is in Z. Okay. So the conclusion then is that TW is linear combination of vectors in Z, but Z is a subspace, right? So hence, in fact, already TW belongs to Z. Okay. So this shows that the subspace Z is T invariant. Okay, so this so this proves the claim. Is everyone okay with this part? Okay, so now let's use this claim to actually show that Z is equal to W. So now we have that V is an element of Z, right? Which is by definition of Z. And remember that the cyclic space W is the smallest T invariant subspace of V of the whole vector space containing this vector, so containing little v. It follows that W is a subset of Z, right? Okay, so this gives us one inclusion. Now we need to show the converse inclusion. So we also know that beta is contained in W, right? So we also have that Z, which remember by definition was the span of beta, is also contained in W, right? Because W is a subspace. So we conclude that Z is equal to W, okay? But this this means we are done, because then it follows that beta is a basis for W, right? So beta is a basis for W. Hence, the dimension of W is equal to J. Okay, the dimension of W is equal to J, and so we conclude that J is equal to K. So this proves A, the part A of the theorem. Okay. Yeah. Okay. So we get the first part. So we have determined what the basis of a cyclic subspace looks like. So now let's use this in order to calculate the characteristic polynomial of the restriction of T to W. Okay, using this explicit basis that we have obtained. So let's do part B. Okay, so here again we just use the definition of a characteristic polynomial. So in order to do it, we have to determine the matrix representations, right? So let beta from part A be an ordered basis for W, right? So we have just established that we have an ordered basis of this special form. Okay, So then we let A0 through A k minus 1 be some scalars in F such that we have, let's denote this equality star, we have that A0V plus A1 T of V, etc., plus A k minus 1 T k minus 1 of V, okay, plus Tk of V is equal to 0. So once again, we know that such scalars A0 through AK minus 1 exist, right? Because Tk of V is an element of W, because W is a cyclic space, right? So in particular, it contains any power of the operator applied to V. So Tk of V is an element of W, and we know that this is a basis for W, right? So it means that there is a choice of scalars AI with this property. Good. Okay. So we have this linear combination representing, well, this trivial linear combination, but it includes Tk of V in particular. So next, let's calculate the matrix representing T with respect to our basis beta. Okay. So we need to determine the coordinates of which vector in the basis, right, with respect to this first. So note that for each vector in the basis beta, we have the following. So we have that the coordinates of T of V with respect to beta are simply 0, 1, and then followed by zeros, right? Because this is just literally the second vector in the basis beta. So hence its coordinates have zeros everywhere except for its position. So 2, in the second position, right? In the second row. Now we can calculate T square. So this is just T of V. So its coordinates with respect to beta are the same as the coordinates of T square of V with respect to beta. But this is just the third vector in the basis, right? So this has coordinates 0, 0, 1, and then followed by zeros. Okay. So we can continue in this way. So let's see the expression for T of T k minus 2 of V, right? So this with respect to beta, this is the same as T k minus 1 of V, right? So one more. So we increased k minus 2 by 1. So this is Tk minus 1 beta. And this is just the last vector in our basis beta, right? So this consists of all zeros except for the last position where we have 1. Okay. And let's calculate one more though. So we also have that T applied to Tk minus 1 of V, okay, with respect to beta. This again is simply Tk of V with respect to beta, right? The coordinates of this vector. And now this we can write as follows. So this is minus A0, minus A1, etc., all the way to minus Ak minus 1. Okay, so where do I get this from? So this follows from the linear combination representing Tk of V in our basis beta. Okay, so let me move the page back for a second to remind you. So remember, this is how we chose these scalars, A0 through Ak minus 1, right? So we know that this is equal to 0, where this is Tk of V, right? But then this tells us the coordinates of Tk of V with respect to the basis beta. We just have to collect these coordinates, okay, but we have to take them with minus because we move this here, and then this gives us the coefficients with respect to the basis, right? So that's it. So this gives us these coordinates, minus A0, minus A1, etc., all the way to minus Ak minus 1, okay? All right. But having obtained all these coordinate vectors, we can now write the matrix, right? So hence, we have that the matrix representing TW with respect to beta is going to be, and here we just have the columns corresponding to the vectors we just wrote, right? So we get 0, 1, 0, followed by zeros. This is the first one here, right? So it goes in the first column. Then the second one goes in the second column. So we have 0, 0, 1, followed by zeros, right? So this is just the second one, etc., right? So I continue placing the columns. So then I have 0, 0, 0, etc., and all the way to 1. Okay. So let's write here dot, dot, dot. And finally, for the final column, I have minus A0, minus A1, right, etc., minus A k minus 1. Okay. So this way we can write the matrix representing TW by calculating the coordinates for T of V, T of V, etc. So we calculated the coordinates of T applied to each vector in the basis beta, and then we just place them as columns. By definition, that's the matrix representing TW with respect to beta. Okay. So everyone is cool with this part? Any questions so far? Okay. Okay. If not, then we are almost done, but we are not actually going to do this part in class. So I leave it as an exercise in the homework. Okay. So the point is that if you have a matrix of this form, then homework, show by induction on K, okay, that the characteristic polynomial of TW is equal to the one predicted by the theorem. So we have f of t, and then we have minus 1 to the power k, a0 plus a1t plus etc. plus a k minus 1, tk minus 1 plus tk. Okay. So the point here is to simply use the definition of a characteristic polynomial. So remember, we know how to calculate the characteristic polynomial of a matrix. Okay. So here you have to show that if, so at this point you can forget everything we did up to now, just have this matrix. And you need to show that for this matrix, the characteristic polynomial is given by this expression. Okay. And the best way to do it is by induction on K. But again, so we leave this for the homework, and yeah. So, but we can discuss it also, of course, after, if you want, after the week passes. Once the solutions are in. Okay. So this was the point. I think the first important step is to obtain this form of the matrix. So to understand that the matrix looks like this, and after this is just additional calculational argument by induction on K for writing that for such a matrix, the characteristic polynomial has this form. Okay, so this would establish the rest of the theorem. All right, so we stop here concerning the proof of this result. So again, the conclusion is that we know how to write out, once we given a cyclic subspace, once we know its dimension, then we can quickly write a basis for it, and we can also quickly write a characteristic polynomial for it using these two results. Okay. All right. So that's the idea. The theorem tells you how to efficiently calculate characteristic polynomials for restrictions of a linear operator to a cyclic subspace. So let's consider an example. So I'm switching to a new page. Example. Okay. So here we consider a linear operator we have already seen in the previous lecture. So let T be a linear operator on the space R cube, okay, defined by saying that T of A, B, C is equal to minus B plus C, A plus C, 3C. Yeah. So we have some operator like this in the example. And let me remind, so last time we have determined the cyclic subspace corresponding to this operator generated by the first basis in the standard, by the first vector in the standard basis. Okay. So let me remind you that we know that W, the span of two vectors, E1, E2. Okay, so this is the T cyclic subspace generated by E1, okay, the first vector in the basis. So this we have calculated in the previous lecture. Okay, so now let us determine the characteristic polynomial. Okay, so now we calculate or compute, yeah, whichever, compute the characteristic polynomial f of t of tw. So t restricted to this cyclic subspace. Okay, so we do it in two different ways. So the first way to do is by using the theorem we just proved. Okay, so using theorem 522. So how to do it? Well, so we know that the dimension of this cyclic subspace W is 2, right? Because it's a span of two vectors, E1 and 2. Okay, so the dimension is 2. Then applying the theorem. And we also know, of course, that T square of E1 is equal to minus E1. Okay, so applying the theorem, we have that 1 times E1 plus 0 times T of E1 plus T square of E1 is equal to 0. Okay, so we have this choice of scalars, which give us 0 when we plug T square E1. Okay, but then once we know the scalars, then by theorem 522b, okay, it follows that the characteristic polynomial can be written as f of t equal to minus 1 to the power 2. So where this 2 is the dimension, right? So this is the dimension, times 1 plus 0 times t plus t square. So 1 times t square, where these coefficients I get from here, right? Okay, and this, of course, 0 times t is just 0, so we get t square plus 1. So this is the polynomial. Okay, this is the characteristic polynomial of TW. All right, now let's do determine the same characteristic polynomial directly. Okay, so by a direct calculation, so let us take beta to be the basis again, E1 and 2. This is an ordered basis for W. Okay. Now, since we have that T of E1 is equal to E2, and we also have that T of E2 is equal to minus E1, we can write out the matrix, right? So we have that the matrix representing TW with respect to beta. So here we write the coordinate of the first one. So this is 0, 1, the coordinates of the vector E2, right? And the second column is going to be minus 1, 0, where these are just the coordinates of the vector minus E1 with respect to the standard basis. Okay, but once we know the matrix, we can calculate the characteristic polynomial as usual using the formula for in terms of the determinant, right? So then we have that f of t, by definition, is the determinant of minus t minus 1, 1 minus t. So I already plugged in the formula for the characteristic polynomial. And if we calculate this, it's of course just again t squared plus 1, right? So we obtain the same answer, but in this case we calculated it explicitly by the definition of the characteristic polynomial, and in the first case we used the theorem. Okay, so depending on the situation, one might be one of these two methods might be preferable to the other. All right. So okay, so this is it around concerning this theorem. Any questions? Okay, if not, we now proceed to the next important result about characteristic polynomials. This is the Cayley-Hamilton theorem. So Cayley and Hamilton are two different people, yeah, two mathematicians. Oops, 1 second. The Cayley-Hamilton theorem, okay? All right, so it's going to give us some information about the characteristic polynomial of a linear transformation. Let's begin with the definition. We need to set up some notation first. So definition, assume that f of x is a polynomial of the form a0 plus a1x plus etc. plus an xn, okay? So let f be a polynomial. And here is just arbitrary polynomial, yeah? So in this definition, I'm not talking necessarily about the characteristic polynomial of some operator, just any polynomial. So let this be a polynomial with coefficients in f, okay? So ai, all of the coefficients ai are elements of some field f. And assume also that T is a linear operator on a vector space V, where V is a vector space over the same field F. Okay. All right. In this case, we want to define what it means to evaluate a polynomial on a linear operator. Okay, so we define f of t. Okay, so I'm going to evaluate my polynomial f on the linear operator t. But of course, this is something that needs to be defined what it means. So we define it simply to be of the form a0 times the identity linear operator on V plus a1 times t plus etc. plus an times t to the power n. Okay. So let me explain what all these things are, what all the symbols represent. Yeah. So where we have that IV again is the identity linear operator. So it is a linear operator. Yeah. Identity linear operator on V. And Tn, as usual, represents the linear operator on V obtained by the composition of T with itself. So Tn is the n times composition of T. Okay, so as usual, as we just used it in the previous situation, so we have that Tn of x, so meaning that Tn of x is defined as T of T, etc. Of T of x, right? Where we apply T n times for all x and V. Okay. All right. So then the point is that f of t itself is a linear operator on V, right? So we have that f of t belongs to L of V. Because look, we have a linear operator here on V, and then we just multiply it by a scalar, which again we know gives us a linear operator, right? Here again, and the sum of linear operators is again a linear operator. So it shows that given a polynomial f like this and the linear operator t, we have defined a new linear operator, f of t, okay, which is obtained by this expression. Let me make a quick remark. So similarly, if we have a matrix A belonging to the space of n by n matrices over F, we can define the same expression, a polynomial evaluated on a matrix. So we can define f of A as A0 times In plus A1 times A plus etc. plus An times A to the power n. Okay. So it also makes sense to apply polynomial to a matrix as we define it like this. So let's summarize what we have defined here. So this is theorem E3 in the book. So assume that f of x is a polynomial with coefficients in f, okay? And assume that t is a linear operator on V. For V, a vector space over F, okay? Then we have the following observations. So the first one, and this is something I already said, but we will check it carefully now. So f of t is itself a linear operator, okay, on V. This is A and B if beta is a finite ordered basis for the space V, and we let A be the matrix representing T with respect to beta, okay? Then the matrix representing f of t with respect to beta is going to be equal to the matrix obtained by evaluating f on the matrix A, okay? So yet again, we see that operations on linear transformations correspond to operations on their matrices, right? So we see that determining the matrix of the linear operator obtained by applying f to t is the same as taking the matrix representing t and then applying the polynomial to it. Yeah. So these two operations commute. Okay. So we have this this result. Proof. So let's see. For the A part, this is basically what I has already said verbally. So part A follows. Since the set of linear operators in LV is closed under multiplication by scalars under composition and under addition. Okay, so we already know that the set of all linear operators is closed under all these operations from before. We know all these things, but now the linear operator f of t is obtained by applying these operations finitely many times, right? So as we see from the definition, we have finitely many applications of the composition, addition, and multiplication by scalars. And since L of V is closed under all these operations, it follows that f of t is also in L of V. This is part A. And for the part B, we are just going to write it out and see that it compares, right? So part B follows by the basic properties. And I apologize, there is some noise in the street. I don't know if you hear it or not. So by the basic properties of matrix representations of linear operators Okay, we have the following sequence of equalities. Let me move to a new page for this. So we have that the matrix representing the linear operator f of t with respect to beta. Okay, so let me see 1 second. There's a question in the chat. So can we assume tk of v for any k less or equal than n is a linear operator? So tk itself is a linear operator, right? Because when you write tk of v, it means you apply a linear operator tk to a vector v, right? So it would be a vector. So tk of v is just a vector in v. But tk itself is a linear operator. And also, of course, it's true for any number. Yeah. So like t, which we can think about as t to the power 1 is a linear operator. Then you can take t square, right, which is just t composed with t. It's a linear operator, etc. So we have that t to the power k is a linear operator for any k. But tk of v, if v is an element of the vector space, is just going to be a vector in it. Should we prove it in the part of the proof? I see what you mean. Okay, so here when we say that LV is closed under addition, right? Is closed under addition. So what do we mean by this? Let me just write it symbolically. So this means that if T and U are two elements in L of V, right? Then we have already defined the linear operator T plus U, which is also an element of L of V. So this is all that we mean by closure under addition, right? But in this case, you can take U to be, for example, T to the power n minus 1, or whichever you want, like A times T to the power n minus 1, whichever, right? So we know that the sum of any two linear operators is again a linear operator. So then in order to show that f of t is indeed a linear operator, you have to apply this in a fixed order. So we assume that tk, yes, we don't assume it, it is true, right? So if t is a linear operator, then tk is also a linear operator. We know this because it's just a composition of k with itself, of t with itself k times. Okay. Okay, Emily, yeah. Okay, good, yeah, exactly. We don't need to assume it. We actually know it's true. We know that taking a linear operator and composing it with itself, any finite number of times is again a linear operator. So it's an element of LV again. All right. So let's go back. Okay, cool. Yeah. When we write power for an operator, it's just composition. That's the usual notation that we use. Yeah. Good. Okay. So let's go back. So we are trying to show that we are trying to understand this matrix, right? So let's just write the expression for f of t given by the definition. So this is a0 times iv plus a1 t plus etc. plus an tn, which is t composed with itself n times, right? Okay, so we need to understand what the matrix representing this operator looks like. Now we know that the matrix representing the sum of linear operators is just the sum of the matrices representing each of them separately, right? And the same for multiplication by scalars. So then we can write that this is equal to a0 times the matrix representing iv with respect to beta plus a1 times the matrix representing t with respect to beta plus etc. Plus an tn with respect to beta. All right. And this is equal. So we know that the matrix representing the identity transformation is just the identity matrix. So then we get a0 times in, right? We get a0 times the identity matrix plus a1 times the matrix representing t with respect to beta, etc. plus an representing t with respect to beta to the power n, right? Because remember, composition, the matrix representing a composition of linear operators is just the product of the matrices representing these linear operators, right? So that's how we get this part, this step. Okay, so we have this, but now this is equal to a1 in plus a1 a plus etc. plus an a to the power n, right? where remember we took A in the statement of the theorem, A is taken to be the linear operator, the matrix representing T with respect to beta, right? So we get this, but by definition, this is just f of A, just a polynomial f evaluated on the matrix A. All right, so this shows that part B of the theorem also holds. Okay, so this gives us the theorem. So now we know how to evaluate a polynomial on a matrix or on a linear operator. And next time, we'll discuss Cayley-Hamilton theorem, which tells us what happens if you take a particular polynomial. So namely, if you take the characteristic polynomial of a linear operator T and evaluate it on T itself. And we'll see what we get this way, okay? So it turns out there's a very nice answer, and this will be the Cayley-Hamilton theorem, which we discuss next time. But that's it for today. So thanks for your attention as usual. And yeah, I'll see you either next time or during the office hours. So thanks, everyone. Bye-bye.